Hi, and thanks for joining our webinar today. My name is Jonathan Fimmer. I'm one of the marketing people here at Waterfall. Our scheduled host for today's webinar was Dr. Jesus Molina, but he is unfortunately sick. So Andrew Ginter will be taking his place today. Thank you, Andrew. This webinar is going to take an in-depth look at the IEC 62443 standard. And it's going to include the IEC 62443-3-2 risk assessments. And we'll also get into why we would need a 62443-2, 62443-4-2 certified components for power generation. Couple notes before we get started. This webinar is recorded. A few days after this webinar, we'll send out an email with a link to the recording in case you missed anything or if you want to share it with a colleague. The webinar is going to be about 45 minutes, followed by about 15 minutes of Q&A, questions and answers. If you have any questions that come into your mind while the webinar is going, please feel free to ask them in the Q&A or in the chat section of the webinar of the Zoom, and then we'll get to those questions at the end if we have enough time. Hopefully we'll get to everyone's questions. And then lastly, if you'd like to learn any more about Waterfall solutions or products, we'll share a link at the end of the webinar from which you can use to have a Waterfall rep get back to you, find out what you need, and see how it could best fit you. So with that in mind, I hand it over to Andrew, who's going to talk to us about engineering grade IEC 62443. Over to you, Andrew.
Yes, indeed. Can you hear me?
Loud and clear.
Okay, good. Yeah, my apologies. Dr. Molina took ill. He is also working on a report that's going to go into these topics in more detail. But that report is probably going to be delayed a couple of weeks as well. And my apologies to his report. I'm guessing he's going to do a much more thorough job than I can, but I'm gonna do the best I can here. So, and everyone on the call, everyone who's registered, will be emailed a link to the report when it comes out. I'm going to talk about 62443. I'm also going to talk about cyber-informed engineering and how we can use cyber-informed engineering to augment, to help out with doing things the 62443 way, with examples throughout in power generation. So let's, with that preamble, let's see what we have here. Let's start with 62443. The standard is, it's a family of standards. It's a family of documents. Some, I don't know, what is it? 15 documents. Only about 6 or 7 of them have been published. The remainder are still being written. It takes a long time. It's a volunteer effort. Anyone on the call who would like to contribute, you do not have to be a member of the ISA to contribute to creating these standards. Go to isa.org or send me email and I'll be happy to connect you to the standards committees. A few words. As Jonathan said, we're going to be focused on the 62443-3-2, which is highlighted in red here. This is for risk assessment, because that's a big way that cyber-informed engineering can contribute to using 62443. We're also going to talk about 3-3, which is the security controls, which in my estimation is, I regard 3-3 as sort of the heart, the brains of the 62443 family, because it talks about what you have to do to secure systems. And this, of course, is the goal: secure industrial control systems. I'm also going to talk about, as Jonathan said, some stuff on the end about using certified components. A few things to remember about 62443, and these are sort of why cyber-informed engineering has an opportunity to contribute materially to installations that are using 62443. A couple of things to remember. One is that 62443 is a standard. It has language in there saying, if you want to comply with the standard, then you must do this, and you must do that, and you must do the other thing. And because it's a standard, must describes the minimum that you must do, excuse me, to comply with the standard. And that minimum changes over time. So the 3-3 standard is currently being updated. Why? Because it's over 10 years old. And the threat environment, as you'll see later in the presentation, the threat environment has changed dramatically in the last 10 years. And so what the minimum that you must do 10 years ago is no longer adequate today. And again, CIE gives us some guidance as to how to navigate that space and figure out what is needed today. A second thing to remember about the standard is that the standard applies equally to large power plants and small shoe factories and everything in between. What does that mean? It means the minimum, the bare minimum described by the standard is appropriate to a small shoe factory. Oh, and so when we use the standard, we have to interpret the standard. In particular, with the risk assessment, we have to select security level targets is the big way that you adapt the standard to different sort of industries and consequences. And so this is the big, part of the big job with applying 62443 is deciding which parts of 62443, how much, basically deciding how much is enough. What security targets do I put in place for the different kinds of networks in my power plants? Because I'm not a small shoe factory. So a few things to keep in mind. What I'm doing here is applying cyber-informed engineering to 62443 in the context of power plants. What is cyber-informed engineering? The quick introduction is that cyber-informed engineering informally is positioned as a coin with two sides. It says one side of the coin is cybersecurity. Teach engineering teams about cyber threats. Teach engineering teams about cybersecurity mitigations. This is what 62443 is all about. One side of the coin is basically 62443. The other side of the coin is engineering. What does that mean? Well, in a large power plant, let's say a coal-fired power plant, old school, old technology, we've got, let's say, 6 generating units. We're producing 1.5 gigawatts of power, 1,500 megawatts. Each generating unit produces 500 megawatts of power. What's a generating unit? Coal dust is fed on a conveyor into a furnace, blown into the furnace. It ignites almost instantly. It's consumed in about a second, turns into carbon dioxide, which we don't like, and of course, water vapor, and traces of other contaminants, and produces heat. Heat's a massive boiler. These things I've seen these things. They're like 4 or 5 stories tall. A massive boiler. The boiler feeds steam into a steam turbine. The steam turns the turbine. The turbine is connected to a generator. The turbine turns the generator, produces power. Imagine that we are the technicians in this power plant. Imagine that we are responsible for these 6 boilers. These 6 boilers are our babies. We calibrate the instrumentation. We replace measurement units when they fail. We've got the gamma ray testers to test for in situ corrosion without shutting the boiler down. We spend 8 hours a day inside the kill radius of a worst case boiler explosion. How would each of us prefer to be protected from a cyber attack that overheats the furnace and causes an explosion and kills us, basically? Would we prefer a mechanical valve where a piece of steel is forced against a spring? If the steam pressure is too great, forces the steel against the spring, the steam escapes, and there's no explosion. Would we prefer a mechanical valve, or would we prefer a a longer password on the PLC controlling the furnace. Most of us would prefer the electromechanical valve. The truly in the know say, Andrew, you're being deceitful here. You've asked the wrong question. The right question is not, do you choose one side of the coin or the other? The right question is, we need the whole coin. I want the the mechanical valve. I want 3 of these things because they're mechanical. They corrode, they wear out, they may or may not work. I want 3 of them in parallel, and I want the longer password, and I want a boatload of 62443 cybersecurity on the side, because this is my life on the line. The engineering profession has powerful tools to bring to bear to manage physical risk. The risk of a boiler exploding due to an earthquake, crimping the steam output valve or the steam output line. The risk of a hurricane coming in, sending too much oxygen into the furnace, overheating the furnace, and causing an explosion. These tools, safety engineering, protection engineering, automation engineering, these tools are applied routinely to deal with physical threat. They need to be applied routinely to address cyber threats as well. They can address cyber threats. Some people are using them occasionally in some places. They need to be used routinely, universally, and systematically to address cyber threats, as well as other kinds of physical threats, cyber threats to physical operations. In particular, where is the overpressure valve in the NIST cybersecurity framework? It's not there. In ISO 27001, no mention of it. Where is that valve in 62443? It's not there. These are cybersecurity standards. We're talking safety engineering, different standards, different things entirely. And so, this is an opportunity to apply powerful risk mitigation tools to the job of protecting physical operations against cyber attacks. Cyber-informed engineering is talking about that opportunity in the context of cybersecurity programs. And, if I may, what's the difference? What's the expectation here? A bridge collapsed yesterday. Big news, people died, horrible problem. Not, to my understanding, anything to do with cyber, but it is a bridge. People expect bridges to carry a specified load for us, in a specified operating environment for a specified number of decades, to do that reliably. This is what we expect of bridges. I heard an expert on the radio yesterday afternoon who designs bridges, and he says, yeah, it was an older bridge. Modern engineering best practice demands that, if at all possible, you design bridges without single points of failure, so that if you knock one of the supports out, the whole thing doesn't come down. And if it's impossible to do that, if there's no way to avoid a single point of failure, then you must address the risks. You must address the threats to those single points of failure and put compensating measures in place, like a large concrete berm around the support. Now, this bridge was 50 years old, but this is what we expect of the engineering profession. What's the opposite of engineering grade solutions? The opposite is IT grade. Imagine that the engineering profession has figured out how to build bridges at a new design, 1/3 of today's cost. Okay, suspension bridges at 1/3 of the cost of today's bridges. The problem with the new design is that it's absolutely riddled with harmonic frequencies. I hope we all remember the Tacoma Narrows disaster back in 1940. One of the world's first large suspension bridges. The engineering profession had not figured out harmonic frequencies. A stiff breeze came up, started the bridge oscillating, and it tore itself apart. Imagine that today's engineers have figured out how to build, I don't know, carbon fiber bridges at 1/3 the cost of normal suspension bridges, but they're riddled with harmonic frequencies. People walking across the bridge starts wretched vibrations and eventually tears the bridge apart. They compensate for that with active vibration dampers. Multiply redundant hydraulics, multiply redundant power supplies, multiply redundant computer systems, artificial intelligence controlling the vibrations. The bridge feels rock solid because of the vibration dampers. How happy would you be driving across the bridge every day if you knew that the design engineer hoped that if a cyber attack targeted the AI, that we could detect the attack before the bridge collapsed? How happy would you be knowing that the design engineer hoped that if we detected the attack in time, we could scramble an incident response team fast enough to prevent the attack from compromising the AI? Here's the thing: hope is not what we expect of people who design bridges. In the physical world, we expect a bridge to carry a specified load for a specified number of decades. In the cyber world, we expect critical automation systems to carry a specified threat load, in a specified threat environment until at least the next opportunity to upgrade our security systems, with a large margin for error. When engineers design pedestrian bridges, I asked an engineer once, how do you design that bridge? They calculate the maximum load of people, shoulder to shoulder, front to back, that the bridge has to carry, and then they multiply by 8, because these are people. Failure of the bridge under load is unacceptable. And so they build huge safety margins in. This is what's expected of us as automation designers and cybersecurity designers when public safety is at risk, when national security is at risk. This is the cyber-informed engineering. So how do we apply cyber-informed engineering in 62443? Well, let's have a look at the 3-2 standard. This is the standard for risk assessment. And if you look at the standard, and I admit I should have looked at this more closely years ago. I only looked at it hard about 6 months ago. The standard defines a process. It says, you have to identify the system under consideration. You have to carry out an initial assessment. You have to partition into zones and conduits. You have to ask, are we done? And if we're not, then we have to do a more detailed assessment and so on. The standard does not say what criteria to use for your assessment. It does not say how to decide, is what I have adequate? In part, this is because, in theory at least, every business has a different tolerance for risk. Small startups might accept more risk than large utilities, publicly owned utilities, because the small startups, well, if they don't make any money in the next 18 months, they run out of venture cap and they collapse anyway. So they're intrinsically high risk. The problem is that we're not talking, most of the time, we're not talking, small shoe factories. We're talking critical infrastructure. We're talking power plants. And so we need a robust, cautious approach to risk assessment. And again, 3-2 doesn't say how to do this. It says the process you have to go through, but does not give you the criteria. And this is where cyber-informed engineering can come in. And before I leave this, I wanted to point out, even the simplest step, the first step in the process, identify the system under consideration, is problematic, because most people say, well, the system under consideration is, I don't know, everything in the OT network, all of the computers that control the power plant. What a lot of us miss is dependencies. Now, I see comparatively few of these in power generation, but the one dependency that I see the most frequently in power generation is Active Directory. our IT teams say, look, if an employee leaves the company, I am required to terminate that employee's permissions company-wide within 24 hours. How do I do that? I need a manager, a permissions manager, identity and access, management, IAM. That's code for Active Directory. I put an Active Directory into my IT network. I put all my employees in there. I'm done. All of my OT systems, if I want to log into the, I don't know, a computer, let's say the HMI server, not the HMI itself, but if I want to log into the HMI workstation to do a backup or something, it's all on Active Directory. Here's the thing. If ransomware gets into the IT network and cripples my Active Directory, I'm sunk. Now I can't log into any of my OT systems. Sooner or later, I probably have to shut down the power plant because I cannot manage the systems anymore. Oh, because I depend on systems in the IT network. Shoot, I had another example. I lost it. Another reason that Active Directory is considered poor practice, IT Active Directory, shared trusts, is that if you compromise the IT Active Directory, you can create new accounts for yourself, and you can use those accounts to log into the OT systems and compromise them. So these dependencies in other industries are a huge problem. They're a little bit less so in power, but you're still going to find these dependencies in some of your sites, especially outside of North America. NERC-CIP effectively forbids shared trusts. But it doesn't really say so. It's confusing. In the rest of the world, you don't have that kind of guidance. You might say my system under consideration that I need to secure is all of my stuff in the plant, not realizing you have these dependencies. So this is something that, sort of CIE aside, this is a problem that you need to be aware of when you're applying these risk assessments and designing your security programs, because the goal is to keep your OT system safe and running. And if you depend on IT services, you depend on IT to stay running, not just OT. And that's an issue, for the company. So when we do a risk assessment, how can CIE help? Well, part of the CIE body of knowledge is safety engineering. And a brilliant book came out about 5 years ago, Security PHA Review. The ISA sells it. ISA creates the 62443 standards. They also publish Security PHA Review. PHA is process hazard analysis. It's a process that safety critical sites in much of the world are required to carry out from time to time. It's a process that everyone else does carry out, whether they're required to or not, because it's just such a good idea. And it talks about how to use the results of a safety analysis to address cybersecurity. And the way it works, I thought I had another slide here. Sorry, I'll just have to wave my hands. The way it works, what comes out of the PHA is usually a spreadsheet. And there's a row in the spreadsheet or a section of the spreadsheet for every consequence we're trying to avoid. The boiler exploding is a consequence we want to avoid. The turbine shaking itself apart is a consequence we want to avoid. And then there's a column for all of the trigger events that could cause the boiler to explode. An earthquake crimping the output valve, and now the steam cannot escape, and the boiler overpressurizes. And then there is a column for all of the mitigations that are in place to prevent the boiler exploding. There's the overpressure relief valve. There's alarms that come up on the HMI, and the operator has been trained when they see this alarm to turn off the fuel flow to the furnace and shut things down. There's safety instrumented systems that can shut down the furnace. So these are all mitigations. And what Security PHA Review teaches us is look at your consequences. If the consequence is unacceptable, if you need it to be prevented, then look at the trigger conditions. If any of the triggers can be caused by a cyber attack, like too much fuel flowing into the furnace, yep, a cyber attack could cause that. If any of the triggers, in a sense, the word they use is hackable, if any of the triggers can be the result of an attack, then look at all of your mitigations. And if all of your mitigations are also hackable, if all of your mitigations can be compromised, now we've got a problem. We've got a cyber attack can cause the event, and all of the cyber attack could also compromise all of the mechanisms that prevent the event. Now we've got to do major cybersecurity. We're talking SL4 grade cybersecurity. These are expensive. This is the most expensive sort of version of 62443-3-3. The recommendation is, if you can, and if you've got one of these dangerous hackable events, put a put an unhackable mitigation in, put an electromechanical mitigation in, like the pressure relief valve, like centrifugal overspeed governors, so that even if a cyber attack causes the problem, we avoid disaster. So that's part of. So this is in a sense, when you're doing your risk assessments, this would be what's called a bottoms-up risk assessment. When you do an initial assessment, you already have your OSHA, your occupational health and safety, PHA review. Use it and see if you can get rid of some of these cyber risks. Just take them off the table with physical mitigations. This is sort of a step that you can do as part of your initial risk assessment. And if you still have, residual risk, if you still have major consequences on the table, now the process, 3-2 says you've got to do a much more detailed assessment. And, most people kind of expect to have to do this anyway. And again, what's identified is the process here, not the decision criteria, the process. So, the process is identify your threats, understand who's coming after us, identify vulnerabilities. And 62443 uses the word vulnerability in a very confusing way. I'm sorry, drafting team should change that word. They don't mean software defects for which there are patches. That's not what they mean by vulnerabilities. By vulnerability, they mean any opportunity to attack a system. It might be a weak password. It might be a misconfigured firewall. All of these are vulnerabilities. Identify attack opportunities. Determine consequences. Determine how important these attack opportunities are because of the consequences they can bring about, and so on. This is where CIE sort of comes into its own. Let's step aside for a moment. CIE says teach engineering teams about cybersecurity risk. And there's a lot of that teaching out there. Here's something that is coming. The 2024 threat report from Waterfall Security is coming in about 2 weeks' time. It's scheduled to publish, I think, the 2nd of April. That's only like 6 days' time. So we're under the gun to get this done. And we've got the data already. It's a matter of writing it up and formatting the result. Here is the data for last year. The threat report looks at deliberate attacks, not errors and omissions, okay, not equipment failures, deliberate cyber attacks that caused physical consequences in heavy industry, critical infrastructure, building automation, and manufacturing in the public record. No confidential disclosures. All of the data here is public. The appendix to the report is the complete data set. If you want to see any of the events that we counted, you can click on the link, go to the front page of the New York Times, and decide for yourself if it was worthy of being counted. What do we see in the data? Well, the decade 2010 through 2019, it was flat. It was bouncing around between 0 and 5 incidents with physical consequences per year. Since the turn of the decade, we've seen a sharp change in the threat environment. 2019 had 5 attacks that met this criteria. The next year was 18. The year after was 23. The year after that was 57. Last year was 68. Most of them were ransomware. 68 attacks that affected over 500 sites. Most of the attacks affected multiple physical operations sites. Most of these attacks were ransomware. Some of the ransomware is very sophisticated. They use sort of the standard nation state style attack pattern. What is that? You launch a phishing attack, you steal some passwords, or you get someone to click on an attachment. If you've stolen passwords, you log in to the IT system and you plant a little malware or something on one of the machines in the IT network. That malware phones home over the internet, or if you've clicked on an attachment, that phones home over the internet. And now you've got a connection from a compromised machine out to a command and control center on the internet. The bad guys, come in at 8 in the morning, Monday morning, get their coffee, sit down. They do this for a living. They're professionals at hacking your stuff. They take over. They look, what have I got? I got 17 machines waiting for me here. They connect to their malware, and they use the compromised machine to figure out what's going on in the IT network to take over other machines in the IT network. They pivot. Pivoting is using a compromised machine to attack other machines and take them over. And eventually pivot through firewalls into the OT network and work their will upon the OT network, usually encrypting stuff. This is the modern attack pattern. Attacks pivot from the internet into the IT network, into the OT network. Some of these ransomware groups are backed by nation states. North Korea is accused of backing a number of ransomware groups because those groups produce foreign currency for the sanctioned regime. Other ransomware groups are wealthy enough to either build their own or buy on the black market nation state grade attack tools. These are very capable enemies. A lot of us might have said, oh, I'm only a 600 megawatt power plant. I'm not. I'm hardly critical infrastructure. Why would a nation state come after me? Well, ransomware comes after everybody with money. If we have money, nation state grade ransomware is coming after us. This is the reality of today's threat environment. How do we use that? Well, we've got to turn that reality into a security level. 62443-3-3 defines these security levels, 1 through 4, and defines the security levels in terms of the adversary. SL1, protection against casual or coincidental violation of security policies. This is like, we're talking accidents. We're talking errors and omissions. SL1 protections, are measures to help prevent, nothing can prevent entirely, to help prevent errors and omissions. SL2 is protection against determined, attacks, deliberate attacks by attackers who don't have a lot of resources, like script kiddies, who download stuff, they press a few buttons, they want to do some damage, but they really don't know what they're doing. SL3 is protection against deliberate attacks that have, fairly sophisticated knowledge and capabilities, but not necessarily unlimited resources. So we're talking ransomware groups. We're talking hacktivists. And SL4 is protection against basically nation states. This is the original intent of these security levels. They're being revisited in part because what used to be criminal groups, what used to be organized crime, ransomware, is now using nation state techniques. SL3 and SL4 in terms of attack capabilities are being blurred. Things that defenses that used to be in the SL4 category in the 3-3 standard really now need to be applied to SL3. And, you know, another problem with sort of traditional risk assessment, traditional use of these security levels is that risk is modeled, cyber risk is modeled as consequence times likelihood. And you can model it in a chart like this, where you can model your consequence on the bottom and likelihood on the top. This is actually from NIST 800-3032, I forget. There's a similar chart in the 3-2 and the 3-3 standards in 62443. I like this one because it's a little bit bigger. It gives you a few more colors. The problem with modern cyber attacks, the problem with these ransomware threat actors is that their success is not random. I mean, when you're doing safety engineering, you're modeling random equipment failures. That's what you model. In safety engineering terminology, you know, CIE is applying safety engineering to cyber. In safety engineering terminology, pretty much all cyber attacks are not random. They are deterministic. They are design failures. How does that work? Well, you know, if we're talking, let's say a power plant. Let's say ransomware gets into the power plant, you know, encrypts a bunch of control system stuff, and we have to shut down. Imagine that, you know, that we bring in the gurus and they identify the affected equipment, take a forensic image to analyze later, erase the equipment, restore from backups, and 6 days later, we're back up. Imagine, however unlikely this seems, imagine we learn nothing at all from the exercise. We got our insurance payout, and we keep going, changing absolutely nothing. If the same ransomware group hits us a month later, what's going to happen? We're almost certain to go down in exactly the same way. It's deterministic. It's not random. And, you know, a second sort of failure, if you apply routine safety thinking to cyber, is that in the safety world, these random failures are independent. If one safety component fails, it's no more likely than before that other safety components will fail, you know, anytime soon. Whereas with a cyber attack, you've got deliberate threat actors going out there, and if they can figure out how to take down one of our safety systems, they will apply that same attack to all 4 redundant safety systems and take them all down. If one goes down, it's very likely that other similar systems are also going to go down. These are sort of, you've got to interpret safety thinking in cybersecurity differently. You've got to take into account that these attacks are, in a sense, design failures. And you've got to take into account that you're going to see multiple simultaneous failures more often than not. This is how cyber attacks work. Okay, so how do we address this? Well, in cyber-informed engineering, it's all about consequences. One of the first steps you have to do in the methodology. And, you know, to be fair, there is, you know, the what's been published for cyber-informed engineering is an implementation guide. And the guide is not a recipe. It does not say, here's how to protect a power plant. The guide is several hundred questions to ask. Some of the questions, you know, I see the guide as more of a framework. Have you thought about this? Have you thought about that? Some of the questions beg the answer. Have you thought about network segmentation? Yeah, I've done that. You kind of know what the answer is. You kind of know, if you answer no, you kind of know that I probably should have answered yes. I better go do some network segmentation. Some of the questions are more nebulous. What's the worst that can happen if a cyber attack takes over the plant? My turbines can shake apart. I suffer $1 billion in damage. Next question. No. What do I do with that knowledge? That's a huge consequence. It's not a recipe for how to do cybersecurity. It's a set of questions to think about. So how do we use that in 62443? Well, we got to figure out the worst case consequences. And then SPR, we got to figure out, do we have electromechanical mitigations in place for these consequences? Because if we do, we can take them out of scope for the cyberspace. A common mistake that people make when they're assessing consequences in power plants is they fail to account for equipment damage. If you hit a relay, you take over a software-based relay, you disconnect the generator from the grid by tripping the breaker in the plant, and you re-engage the breaker a fraction of a second later, the generator has shifted out of phase with the grid, enormous torque is put on the generator, and you risk destroying the generator, or more likely the steam turbine. If you again manipulate the relays, it's possible to send, I don't know, too much power, or it's possible to manipulate the transformers and damage the transformers. Here's the thing: what people neglect to consider too often is that if the bad guys can pivot from the internet through the IT firewall into the IT network, they can pivot from the IT network through the OT firewall into the OT network. They got through the IT firewall to get into IT. That's one layer of firewall. They can get through other layers of firewalls. The problem is that protective relays that protect our equipment are hackable. Think about it. What do we do when the overpressure relief valve to prevent the boiler exploding, when that engages? What happens? We shut the generating unit down. We might shut the entire plant down. Why? Because the last ditch safety, the last safety standing between us and disaster, just engaged, saving our lives. That's never supposed to happen. All of the other systems we have in place are supposed to prevent that outcome. We shut the plant down to figure out what just happened. How did it happen? Why did it happen? What are we going to do to make sure this never happens again? And we've put national security at risk. What do you mean national security? A 1.5 gigawatt power plant is critical infrastructure. The legal definition of critical infrastructure is critical to the nation. That's the legal definition. We've put national security at risk by shutting the plant down. We don't want that. How can we prevent not just disaster killing people at the site? How can, not just destroying equipment and shutting us down for months until the turbines can be, rebuilt? How can we prevent safety shutdowns in the first place and keep the lights on? Well, one of the ways to do this is, we need to translate consequences and attack knowledge. We need to translate that into a security level. That's what 62443-3-2 says. That's the minimum we have to do. What I suggest, what cyber-informed engineering, that perspective suggests, is that, because cyber threats are deterministic, not random, the right way to model risk is as something called design basis threat. This is a concept from physical security. If you're building an embassy in, I don't know, Iran, or someplace where there's a risk of terrorist attacks, a design basis threat document is a document that describes the most capable adversary that the security program is required to defeat reliably. It might, I've never seen one. These things tend to be classified. It might say you are required to defeat reliably 4 terrorists armed with submachine guns and hand grenades trained for 3 months at this base in Iran. You're required to defeat that reliably. You're not required to defeat a squadron of tanks driving down the street blowing holes in buildings. So this defines the most defines the most capable threat that you have to defeat reliably. Here's the thing. What we see a lot of power plants doing around the world is saying, look, the pervasive network threat is nation state grade. It's nation state grade ransomware. If they can get in, they will get in. We need engineering grade protection against that threat. And so they create a design basis threat statement, a definition saying, here's what we're going to design to in our risk assessment. We're going to design physical processes, automation systems, and networks. We're going to design them such that no internet-based attack can pivot through intermediate networks, can reach our safety critical systems, cannot reach our reliability critical systems and put them at risk. That's engineering grade prevention of the propagation of cyber attacks. How do you do that? This is what network engineering is about. This is my new book. I forgot to mention, I think the URLs from these books are being posted in the chat. So the threat report will be available in a week's time. You can sign up for it now. It'll get mailed out to you when it's available. The book free copies are still being given away by Waterfall. It's a book about engineering grade protections. There's a whole section in there on network engineering, and some examples of network engineering. The textbook example is the EPRI, industrial internet. The PhD, EPRI is the Electric Power Research Institute. It's a few hundred PhDs that do research on electric power. They were asked a handful of years ago. They were asked, how can we use the industrial internet safely on our very large steam turbines? Because what is the industrial internet? The killer app is predictive maintenance. We want to send vibration data out to the vendor so the vendor can tell us what's wearing out and how to manage these very expensive, very big devices optimally to reduce our maintenance costs. And so they came back with and said, well, here's what you do. You take the measurement devices, the industrial internet calls them the edge devices. Do an engineering study on the edge devices, prove that they cannot control anything. They are truly monitor only. That's the only thing they can do. And then deploy them on your steam turbine, start measuring, and connect them out to the IT network. Connect them to a DMZ on the IT network, stick some SIM cards in them, connect them straight out to the internet if you want. Do not put them on your control network. Now, what's the worst that can happen? You can compromise the devices. You can maintain your systems suboptimally. It'll cost you a few $1 million. You can buy insurance for that. Okay, you have not put the entire control system at risk by carving a connection from the control system out to the internet. This is an example of network engineering. It's a way to do what otherwise might seem a very dangerous thing safely, because you've engineered the networks in such a way that they're, a compromised edge device physically has no advantage in terms of compromising the rest of the control system because it's connected to a different network. The most common example of network engineering is not the EPRI methodology, it's the unidirectional gateway. This is what Waterfall produces. For anyone who hasn't seen it before, it's used absolutely routinely in power generation, tends to be used in the largest plants, the most consequential plants, the ones that are most consequential to the business, the most consequential to the nation. The hardware is physically able to send information in only one direction. What does that mean? There's under the hood. Do I have a diagram? No. Under the hood, there's a circuit board that has a fiber optic laser, a transmitter. It sends to a second circuit board that has a receiver. You can send from the industrial network out to the outside world. It's not physically possible to send anything back because there is no laser in the receiving circuit board. So physically able to send only one way. We can send stuff out to the internet. We can send stuff into the IT network. We can benefit from access to OT information for business automation without risk to the OT systems. And the software, by the way, replicates servers. If you've got a Pi server in the plant, in the power plant, the software logs into the Pi server, asks for the latest data, pushes the data out, and pushes it into an enterprise Pi server. It's not a firewall, but it sits at the IT-OT interface. It's a way to get access to OT data without getting access to OT systems, without putting those systems at risk of a pivoting attack. You cannot pivot through a gateway. So some examples of network engineering, other engineering grade mitigations that we should consider. Hardware security modules are basically bump in the wires. These are devices that do encryption that are physically separate, that have the encryption keys are not in memory in hosts. They are in these hardware security modules. Trusted platform modules are part of modern CPUs that, again, hide encryption credentials so that they cannot be stolen by malware, even if you want to steal them, even if you've taken over the machine. Certain very sensitive information like your encryption and authentication credentials are physically separate. Write once, read many storage, or otherwise tamper-proof forensics. If you need a record of how the bad guys got into your IT network, and you want that record to be so that you can close those holes, you want that record to be tamper-proof so that the bad guys cannot erase it, use hardware signaling, like a unidirectional gateway pushing the data into a disk drive, or using the old style write once, read many, DVD drives. We see analog signaling being used. You can run a 4 to 20 milliamp current loop out of your safety system to report the status of the safety system. You don't need to connect the safety system to the OT network and put the system at risk. You can just report those statuses through analog signaling. So there's a host of these. Part of the job of CIE in the next 12 to 18 months is to put together an inventory of all of the different kinds of electromechanical hardware-based mitigations, unhackable mitigations, be they technology or procedural. That's part of CIE's job. And our job as applying 62443 is to go through our risk assessments and ask the question, where can we use these things very early in the process to eliminate risk rather than try to reduce risk later on with 62443? What's left after we apply network engineering is residual risk. Well, if the bad guys cannot get in from the network, now we have to ask, what other risk is there? There's the risk of insiders. They might make mistakes. They might, have an axe to grind. They might have been deceived by ransomware actors, and they're carrying something in on their USB. They might be blackmailed by nation states. Okay, these are all, and we have to decide, the engineering function has to decide which of these risks, which of these threats are credible. Not all threats are credible. 3-2 says we should assign a security level to each of our network zones. Well, I think we need, what CIE recommends is a subtler solution. The network connection between the OT network and the IT network, that has to be secured with engineering grade protection if the consequences of compromise are unacceptable. And for large power plants, they are unacceptable to the nation. The consequences are unacceptable. We need network engineering at that interface. That's essentially SL4 or SL4 plus at that one interface. Does it mean the entire zone has to be SL4? Well, no. The connection between that part of the OT network and other parts of the OT network, that can go through a firewall. Your insider threats are generally, is it credible that the Russians are going to plant 3 spies into your workforce in the power plant, and the spies are going to sit there for 10 years as sleepers, and they'll get activated in 10 years' time? For some power plants, feeding power into, the Pentagon, that's a credible threat. For other power plants, this is not a credible threat. SL4 is not what we need for the rest of our zones, or even for the rest of that one zone where we've got an SL4 network mitigation. And so what we need to do is understand our threats, just like 3-2 says, and decide how thoroughly we're going to protect. Create a design basis threat directive saying which of these threats we're going to accept, or we're going to, do what we can, but, no guarantees, and which of them we're going to do our very best to eliminate. This is part of the planning process. It's subtler than one security level throughout. It's, sometimes it's stronger than one security level throughout, and sometimes it's weaker and more affordable because we can justify less defenses with a clear design basis threat directive. I want to say one more thing, and I'm running out of time. A lot of us are requiring 4-2 certified. The 4-2 standard is a certification for devices. A lot of us are requiring certified devices. I just want to be sure that, when we do that as part of our risk assessments, as part of our purchasing strategy, that we understand what we're getting. In my understanding, I think it's all. I haven't actually looked at a list, but I'm assured by experts that pretty much, if not entirely, all devices that have been certified to date against the 4-2 standard are certified to SL1. What does that mean? Well, SL1 says the device gives you some accounts and passwords. They may be shared. Gives you, if you're logged into the device, gives you a lock screen if you go inactive and you got to give the password again. Gives you some logs, security logs. Someone just logged in, someone just logged out. Does some input checking. Gives you, features that they're not very secure. They're basically, a little bit of protection against, errors and omissions. SL2 gives you a bunch of stuff, including encrypting your passwords, including signed firmware, so that if somebody logs into the device and says, here's a new version of firmware, they can't just upload it. Includes secure boot, saying, I'm only going to boot if the firmware is signed. If all you have is an SL1 device, your connection to the device where you're communicating with it is not required to be encrypted. The ability to load new firmware into the device, like all zeros, bricking the device, is not required to be password protected, is not required. The device is not required to reject the firmware because it hasn't been signed. Advanced security features are not there. It's the very basics that you're getting. Now, does it make sense to require 4-2 devices? It probably does, because these very basic features, you kind of do expect, don't you? Just when you be cautious when you buy an SL1 4-2 certified device. Understand that you're not getting major cybersecurity. You're getting sort of basic features that everybody expects, and everybody does expect these features. So go ahead, just understand what you're buying. That's what I had for you. I hope it makes sense. In short, threats to worker safety, threats to national security are unacceptable. We need to deploy engineering grade defenses for those threats. We need to evaluate what's left over. Once the network engineering is in place, we need to evaluate what's left over in terms of residual risk and choose carefully from the 3-3 standard. Helps if we have a design-based threat directive that we can select against. CIE gives us perspective on threats and on consequences and on how to do security targets. And certification is about basic functionality today. By all means, require it, but don't kid yourself that having required certified devices, you've got strong security. What you've got is basic functionality. The goal with engineering grade security programs is to carry a defined threat load, defined by the design basis threat, reliably until at least the next opportunity to upgrade, with a large margin for error. This is the goal. This is what I have for you. Jonathan, do we have questions in the queue? I know we're running a little bit late.
Yeah, Andrew, we got actually a whole bunch of questions, way more than normal. I guess a lot of people are curious about this topic. Some of the questions I see some of you asked are very specific towards a specific type of technology that you're using. I ask you, there's a link towards the end that we're going to share now, I believe. It's already shared there. If you could request in that link and speak to a specialist, because it might really only pertain to that technology. We did, however, get, it was 4 questions here that are directly, I think, relevant. Um, I know right before the call, I asked Andrew a little bit something for something else I'm working about, air gapping solutions. I see someone asked a question about that, and that was the first question in the thing. And he asks, uh, Ryan Baguette, do you recommend air gapping solutions such as tempered networks, now Johnson controls, Airwall?
Um, Good question. I'm not familiar with Airwall. I'll take an action item to look into it. I will say that the word air gaps is extremely confusing. Um, in the old days, air gaps were physical gaps. The way, there was no such thing as, routine wireless. Signals passed between computers on wires, not fibers, on wires. And, the electrons moved in the wires. An air gap had, power coming into the computer, but no wires, or power coming into a network, but no wires connecting the network to the outside world. There was no online information change with the outside world. Those air gaps disappeared 30 years ago. This is ancient history we're talking about in most sites. Most sites that think they still have an air gap today, when you do an audit of connectivity, they find dozens of connections to the outside world. Why is that? Well, partly it's just history. We didn't pay attention to the connections the vendors were sticking into these systems. We forgot the connections we stuck in there ourselves. Part of it is terminology. I'm an old man. Okay, I'm a grandfather to, as of a week ago. I'm an old man. Um, the young folk today are using the term air gap to mean cannot route a packet from this network to the internet. That means the network is air gapped. It might still have a firewall. The OT network might have a firewall to the IT network, has a firewall to the internet. If the IT OT firewall says no packets can go from the OT network to the internet, it has no, has denied by default. They call it an air gap. And so us old managers talk to the young folk and say, what's our security look like? We're air gapped. We're good. And we think it means the old meaning of air gap when it means the new meaning, meaning you can still pivot through firewalls and take over the system. We misinterpret what we hear. So the term is very misleading. I'm not familiar with Airwall. I'll take an action item to look at it and, maybe, I don't know, put a blog post out or something explaining, how that fits into the discussion here.
Okay, thank you, Andrew. We have another question that was asked also early on in the webinar. And they see they called Waterfall a firewall. So I'm reading what they say here. How does the Waterfall firewall different from the NGFW current Tub 5 like Palo Alto?
Next gen firewall.
Yeah, okay.
Yeah. So the big difference between the Waterfall unidirectional gateway and a firewall, there's a couple of big differences. One is that the gateway is hardware enforced. It's engineering grade unidirectionality. Nothing can get back. With a firewall, if you configure the firewall correctly, then no attack should get from the IT network into the OT network. With the unidirectional gateway, it does not matter how you configure it. Nothing can get back. This is the difference between engineering grade and IT grade solutions. The unidirectional gateway is engineering grade. A next-gen firewall is IT grade. Don't get me wrong. There's a role for next-gen firewalls. You have firewalls inside the OT network, typically dozens of them. You have firewalls on the IT network, typically another dozen of them. You put one gateway in place at the criticality boundary between the network with business consequences and the network with unacceptable physical consequences. That's where the gateway goes. The gateway is unidirectional. The gateway is also different from a firewall in that firewalls are routers. Oh, the firewall vendors, they're going to shoot me. Firewalls are much, much more than routers, but built into every firewall is a router function. Because what does the firewall do? It looks at every message coming in and it asks the question, is this message allowed? And if it's allowed, it hands the message to the router function saying, send this where it's going. That's what firewalls do. They forward some messages from one network to another, and they drop others. They are routers. The gateway is not a router. The gateway makes copies of servers. It's usually a client on both the IT and the OT network. It's a client of the OT Pi server or the OT OPC server or some other server on the OT side, logs in, once a second, asks for everything that's new, gets that snapshot, sends it out through the weird one-way hardware, and on the outside populates an identical server. If it's Pi on the inside, it's Pi on the outside. If it's OPC on the inside, it's OPC on the outside. Now, the hardware says nobody on the outside can send any questions back into the OT network. The software says nobody on the outside needs to send any question back into the OT network because all of the data that's allowed to be shared with the IT network is out there already, and you can query the copies for the data. We have white papers on this too. So, you see my email on the bottom of the screen here. Drop me an email. I'll send you the comparison between firewalls and gateways white paper. It goes into a little bit more detail, but that's the key idea.
Okay, thanks, Andrew. And we got a lot of questions here. I don't think we'll be able to get to all of them, but there's a few here I'm going to pick because I think they're fairly universal in these questions. So first one, and this should be, I don't know if it's a short or long answer. What is the level of certification on Waterfall equipment?
We are certified by a number of different authorities to different standards. Full disclosure, we are not yet 62443-4-2 certified. We are certified common criteria to EAL4. This is a military grade certification for security components. We are a civilian supplier, but some of our customers, the largest power plants, asked for the military grade certification, so we got that. We are certified, in a bunch of local jurisdictions, Singapore's NITES, Israel's ANSI. We've got a ridiculous number of certifications. Sooner or later we're going to have to get 62443. But it's a steady diet of certification work. So if you, again, send email and we can send you a comprehensive list if you're interested.
Okay, and I like this particular question. Someone asked her because on my first day in Waterfall a few years back, this was my question when I first came here. So I'm going to ask this person's question. What if a control action is to be taken from cloud to the ICS plant in case of a unidirectional gateways?
What if a control action needs to be triggered by the cloud? Most of our customers absolutely forbid that. Absolutely. Why? Well, most industrial sites nowadays are connected to a dozen, in the power gen space, maybe a half dozen vendors. In manufacturing, it's closer to 100 vendors per plant. There's a lot of cloud connections. Some of those vendors are well defended. Some of them are poorly defended. All it takes is for the bad guys to compromise one of the poorly defended cloud sites. And now they've got an opportunity to download new firmware, to send control commands into our power plants, into our heavily defended power plants, through encrypted connections, punching through 7 layers of firewalls into our plants to control physical operations from the cloud. How many computers in the cloud should be able to reprogram our safety systems? What kind of question is that? Well, if you can take over a device from the cloud and pivot from the device into the safety system, you can reprogram it, can't you? Oh, yeah. So that's the short answer. There is a longer answer. There's always something that needs to come back in. So the classic example is predictive maintenance. Okay, the turbine vendors do not press a button and control the turbine from the cloud. What they do is they pick up the phone and they call and they say, you've got a vibration problem building up on generating unit number 3. Can I have an hour Thursday to work with you to fix the problem? Sure, we schedule them. 3 o'clock Thursday comes, we call the vendor. So we know who we're calling, we know who we're talking to. And we say, you ready for this? The vendor says, yep, I'm ready for this. And an engineer is sitting down in front of the turbine vibration workstation and turns on remote screen view and starts taking pictures of the screen, just like you see pictures on my screen over here, being transmitted to you on the Zoom call here. Starts taking pictures of the screen and sends basically a video of the screen through the one-way hardware out to the vendor. Now the vendor can see the screen. Now, the vendor can bang on their keyboard, they can move the mouse. Nothing gets through the one-way hardware, but they're on the phone and they can say to the engineer sitting there, okay, let's bring up vibration diagnostics, and they can see the mouse move and they can go, no, that's system diagnostics, 2 further down. There you go, that's vibration diagnostics. In real time, they're giving the benefit of the vendor's advice and expertise to the site. The vendor thinks they're supervising the site in the course of a complex correction according to the vendor's processes and procedures. The site looks at it differently. The engineer is not a mouse monkey. The engineer is, whose turbine is this? It's ours, thank you. We want to know what you, the vendor, have done to our equipment. And so the engineer is going to move the mouse when they understand why they're moving the mouse and when they understand why this is the right thing to do to their device at this time. The vendor is asking questions. Sorry, the engineer is asking questions. The engineer is taking notes. The engineer thinks they're supervising the vendor. This is the right solution when you have external expertise that you need to leverage inside the plant, but that expertise is coming from, let's call it, untrusted sources. Has the vendor been through the site's criminal background checks? No. Has it been through the site's safety training? No. Have they been through the site's security training? No. Then if they showed up physically at the site, they would not be allowed to go into the site and touch whatever they want. They would be escorted every second that they're in the site. This is supervised remote access. It's the right way to deal with cloud-based vendors who want to touch our systems. There's other solutions for getting information into the system. There's always information that has to come into the system one way or another. And the question is, define the design basis threat, define the threats, and wherever practical, put engineering mitigations in place. I talk about most of this in Appendix B. If you want to dig into the new book, Waterfall's giving these things away. Appendix B has 20 design patterns for unidirectional networks to address questions like remote support, inside a remote support versus outside a remote support, continuous remote operation if you have a remote operator, and so on. These paradigms are all there.
Okay, great. Thank you. And there was another question someone asked, and you actually answered it there. So we got through a good amount of questions. We actually, I think, have a record of questions, over 20 questions this time. I've never seen that many questions one of our webinars. So great job. Shows that there's a lot of interest, a lot of people working on this.
So what you're saying is that I've got a lot of work ahead of me answering these questions in email.
Some of them are overlap, which is also a really good show.
Good for me. Good for me. Thank you.
And then also, I could see some of them are very pertinent to just, either one very small group of people or to one or two customers or whoever's asking that. It's not something that's going to be universal, but there's clearly a lot of people.
I hereby commit to getting answers back to every one of you. It may take a few days. I'm overseas for the next 3 weeks, but I will get back to you. Thank you for your interest and for your questions.
Okay. So, I mean, we're a little bit over the time. So thanks everyone who joined us, and thank you all for the questions, especially the questions, since those were a lot. As I mentioned earlier in the beginning of the webinar, if you'd like to speak to a Waterfall rep about any of our solutions, or if maybe you want to ask those questions to one of our reps, there's a link that's in the chat that get that process started. We'll also send out an email in the next few days with a link to the recording of this webinar, in case you want to share with anyone or watch it again, or if there's anything you missed or want to cover. And thank you again, everyone, and thank you, Andrew, for covering for Dr. Molina, who we hope feels well soon. And I think that wraps it up. Have a great day. Anything else, Andrew?
It's all good. Thank you, Jonathan. Thank you for driving this. Thank you, everyone, for attending. Thank you for your keen interest. I will get back to you. If you're interested, grab a copy of the book. We ship to most parts of the world. We don't ship to all of it. My apologies. If you read the thing, drop me a note. You've got my email, firstname.last@waterfall-security.com. I'm always looking for feedback. I'm always trying to figure out, is this material useful? What would, what shall I write about next is a question. And if there's issues with it, and I've already found issues in chapter 6, identify them so that we can work on gathering knowledge from the world's experts. I don't make up most of this stuff. I repeat what I've learned, and try and get the word out. So feedback is welcome. Thank you all.
Thanks, everyone. Thank you, Andrew. And everyone, have a great day. We'll see you next time.